Hello, my name is Katya Bazilevskaya, and I am a staff scientist at Material Characterization Lab. This video will give you an introduction to the automated imaging technique to measure particle size and shape. Automated imaging determines particle size, shape, and other physical properties such as transparency. This technique allows to see each particle in details to reveal the presence of agglomerates and particles with irregular shape or rough surface. We can also get statistically representative size distributions because thousands of particles are obtained in one measurement. Automated imaging is often used in conjunction with other particle characterization techniques to gain a deeper understanding of the sample or to cross-validate particle sizing methods. Automated imaging techniques use digital camera to capture 2D images of a dispersed particulate sample. They can be divided into two types. In dynamic image analysis, particles flow through the field of view of the camera, so particles dispersed in water are captured during the movement. In static image analysis, particles are dispersed on the surface, pictures are taken from stationary particles, then a slide with particles is moved to take multiple images at different positions. Static imaging systems are more flexible in terms of sample presentation and having ability to reanalyze exactly the same particles, while dynamic imaging systems offer advantages in speed of measurement and ease of sample preparation. The system we have at MCL is a static automated imaging system. The workflow consists of the four main steps. Step 1. Sample dispersion. A proper sample dispersion is very important to obtain good result, and dispersion procedure should be optimized according to the material type, particle size, and type of the dispersion, whether it's wet or dry. The goal is to have enough particles separated on a slide, like you see on the left image, and particles should not be crowded and overlapped as it's shown in the right image. The second step is to choose region of interest and magnification and start scanning. The system scans over a region of interest and captures images of individual particles while keeping particles in focus. Dynamic changes in size or shape distribution can be observed during the scan. Step 3 is image processing or image thresholding. Image thresholding is a partitioning of image into foreground and background. This image analysis technique isolates particles from the background by converting grayscale images into binary images. And the final fourth step is results generation. There are some common size parameters that are reported for each particle. Particle size can be expressed as circular equivalent diameter, which is a diameter of a particle that has the same area as a particle of interest. Length and width are also used to express particle size. Aspect ratio and elongation are the most common parameters to describe particle shape. Elongation is 0 for a perfect sphere and 1 for fiber-type particles. Circularity and solidity shows the degree to which the particle is similar to a circle. For example, the further away a particle deviates from a perfectly round, smooth circle, the lower the circularity value is. To give an example how to use the data obtained by automatic imaging, I want to illustrate the following study, which was focused on the comparison of two stainless steel metal powders obtained by atomization process. Atomization is a process of formation of metal particles from molten metal using a spray of either liquid or gas. Sample A was prepared by gas atomization, sample B was prepared by water atomization. Both samples have a same size distribution. This is parameter variability plot showing the degree of difference between the two metallic powder sample for each parameter analyzed. The green bars are related to the particle size and the red bars to the particle shape. The length of each bar indicates the degree of difference between the samples for each parameter. Clearly, there are minimum differences between the two samples in terms of size parameters, but there are differences in terms of some of the shape parameters, in particular elongation and aspect ratio. A scatter plot or scattergram is used to observe relationship between variables. Each dot represents values for two different numerical variables. In our case, circular equivalent diameter on x-axis and elongation on y-axis. For individual particle, comparing these two scatterograms, we can see differences in elongation between samples produced by different atomization techniques. Water atomized sample contains more irregular particles than the gas atomized one. Despite the two samples having the same particle size, differences in particle shape identified between the samples may result in difference of powder performance. In summary, there are following advantages of automated imaging analysis. First, you can see individual particles, size and shape. No model assumptions are required. Then we can get number-weighted particle size distribution and can analyze fine particle in the sample. We have software-controlled dry dispersion unit for better dispersion and can obtain statistically representative number of particles. Disadvantages include longer measurements compared to laser diffraction. Results may depend on the choice of magnification and threshold values. We can observe poor contrast for some materials, and also for particles suspended in liquid, we can see diffusion at higher magnifications. Typical applications include metal and mineral powders, coals, sand, plant material. Also, this technique is used to validate laser diffraction results. These are technical specifications for our morphology G3 unit we have at MCL. You can look into more details on our website. Please contact me if you have any questions. Visit our website if you want to submit training or analysis request. And I hope to work with you in the future. Thanks.